Last week, we started BJTs. As you guys go through the homework of BJTs, it's very important that you distinguish the operation modes of BJT from the operation modes of MOSFETs. If you remember correctly, in MOSFET, we use saturation for the flat part of the current, but we use triode for the linear portion of the MOSFET operation. But in BJTs, we use active region, or sometimes we call it linear region for the BJT operation. Then we have the saturation region is a nonlinear region that we don't usually use very much. So if you guys remember the curve that we had for MOSFET, and then we call this one is a saturation region, and we call this one a triode region, and then the saturation region. So you have the corner area with the current when you change VDS, that is called a triode region. When you move on to the flat portion, when the current is constant for a given VGS, that's called a saturation region. In electronics, we mostly use the saturation region for MOSFET. But then for BJT, the names are just slightly confusing as you guys move this along. So we have this one, and then this one we call saturation region, and this one we call the active region. One being the saturation, but it's the thing that we don't really operate. But in BJT, in MOSFET, saturation is the region that we mostly operate at. Like T saturation is the one that we actually don't. Now, if we go on to the relations for BJTs, we mostly operate this in active region. And we have a very simple relationship between the three currents. Basically, if we start talking about VB, so let's draw a symbol here. Taking NPN type of BJT as example, if VB no current. So B to E is a positive PN junction. So if that junction voltage is less than 0.7, which is a diode forward voltage, it's going to be in off stage. The collector voltage is less than 0.3 volts. We call this in saturation region. If VCE is larger than 0.3 volts, we call this one active region. So this is you jump. This thing is going to work. The diagram. The VCE is roughly 0.3 volts if you look at this region here. If you guys follow my writing. So between the origin of the coordinate all the way to where the current becomes flat, that region is called a saturation region. And the voltage between collector and an emitter is about 0.3 volts. Okay. Mostly, we're going to look at the active region when we move on to amplifiers. But of course, in this particular class, you need to understand how to, you need to know whether it's off mode, on mode, saturation mode, or active mode. So you need to know. If I give you a circuit, you do some calculation, you can understand, oh yeah, this is in off state, okay, or it's in saturation state, or it's in active state. Well, even though the active state is what we want, but we still need to understand how to design the transistor so that it is in mode. Okay? So similarly, if you move on to a job where you want to design an integrated circuit or just simple amplifier for some speakers, whatever. And when you design the circuit, you need to check if this thing is in active mode. If it's not in active, your design is flawed, not going to work. Okay, so that's why it's important to understand, even though most of the analysis moving on, we're going to focus on the linear, the active mode, but we still need to understand how to make this thing work in that mode. Okay, clear? Good. So now, if we in the active mode or in the active mode, and there are a couple relations you need to memorize. So one is this IC is equal to alpha times IB. Sorry, not alpha, beta. Let me see. Well, I write this, got this wrong. Okay. So IC is beta times IB. And this beta value is a typical value for microelectronics, typically about 100. Of course, in some problems, you might see 50, you might see 10, you might see 500, but 100 is typical value. I would say 95% of BJTs would operate for microelectronics game. They would operate around 100, better it's around 100. That's really a very, very typical value for a BJT. Of course, if you look at the circuit, it's like a big node, BCE, there's 3 branches. So the BJT becomes like a super node. Okay? So if you look at here, and you summarize the current relation, say, well, IE is going to be IC plus IB. So, and then if you take the relations between IC and IE and IB, so you can pretty much vary the relations all these 3 currents. And this definition of alpha, which is beta over beta plus 1. And this number is roughly typical value. If beta is 100, beta plus 1. So it's about 99. And then if you look at this, then current IC is going to be beta times IE. So ideally, as IC, you got IE. So because this is very small, so IC and IE are almost like the same. It's only 99%, only 1% difference. So actually, it's smaller than a MOSFET. So remember MOSFET, we had that pretty complex 1/2 kWL, blah, 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 right? But this equation is much simpler. So I would say equation is simpler. It doesn't mean that it is simpler to analyze, because later on we're going to look at some of the examples. You're going to see, well, to some degree, you might think it's simpler, but to some other aspects, it might be actually more complex, depending on what the problems we're dealing with and what we are doing. So this one, some of the relations of different currents. So you guys need to remember those or write them down so that you can reference them. But in addition to those 3 current relations, we also have one more equation you guys need to remember. It's the top one, IC, this one here. So I'll write down, we write this many times. What is the current? Well, this current is actually the current we see many times is in the diode current. So IT is 25 millivolts at 25 degrees C, which is called summer voltage. Because when we move on to this small signal model, then what's changing? If I just change a little bit IB, what happens to IC? We need to get back to this equation. Otherwise, we just couldn't. Those equation on this side pretty much describe the large signal model, where we're looking at DC, Y, What happens when you add a small value to VB or add a small value to, so this is, oh. Now let's look at, now since there's a simple relation in active mode, we want to look at how we can represent that circuit, represent that BJT with a, so since we know that IB, again, we want to write the equations here. So if we write IB equal to IS times E to the VBE over VT. So if you look at this equation, what would you say? Oh, what shows IB? So typically VT is a constant for a given temperature, just VBE, because this normally also kind of fixed when the device is designed and manufactured, related to the area, size, all the pure impurity, all that kind of stuff of the silicon or semiconductor. So the only variable that changes is VBE. So you can imagine that if I change VBE, IB will change. So IB is controlled by VBE. So IB is kind of a controlled source by VBE. So that's one thing that we need to understand, right? And secondly is that if IB is given, once IB is calculated, we can find IC is better times IB. So what we are saying here is IC, yeah, it is a current, but it's not a current by itself. It's a current controlled by IB, and the ratio is multiplied by beta. So in the sense that if I write IB as a current source, and I can write IC as another current source. So basically, if I sort of go to the way that we write it, it's like this. If I can write IB, you can write IC. If I write IB, right? And IB plus IC equal to IE. So therefore, you sort of can write a very simple diagram where you have IB coming in, and IC is beta times IB, which is controlled. This IC is going to become a controlled source like this. So it's a diamond because it's IB. So if you change IB, IC will change. And at the bottom, you have IE. So do you think, that is very simplified model for BJT? But on the other aspect, we have equation number one says, well, IB is also controlled by something else. It's not just by VB. So how do you present VBE in that equation? Is that, well, we know how to come up with this. The first model says you get IB coming in, and flowing down is at IE. So IE is IS divided by alpha, and the top is IS times E to the VB times VT, and the stage between. So that is the same equation I draw on the top right corner. It's just I replace the IB with what give one, and we can come to understand. What are we really doing? that equation over there. So IB equal to IS times that e to the power something, right? So, on this, and you have IE. So IE equal to IB plus IC. Now, why draw a diode? Because that equation number one is exactly the current of a diode. So therefore, we basically just draw this diode in place of that equation. Okay, so that's this equation. And yeah, so let's move on. And again, as I said, if you guys have hard time understand this, we can come back later. Look at the example. N-type transistor. We can sum of the number and beta. Those are the two that are given. So by that is given, and so basically, this is what we're saying is this is 5 volts at the top, and it is fed with a current source at micro, and we will find, yeah, we need to find VT, and we also need to find VBE. So let's put a ground over here. And of course, the second question is that replace the current source with a resistant connect from the base to the 5 min and what happens? So we can go to the next slide to do that problem. Looking at this problem, it did say that this transistor is going to work in active to whether the thing is going to be in active mode. So it is in active mode. Basically, what it says that IC is equal to beta times IB. So when it says active mode, that's what it means. Once we get to the next few slides, and we're going to see there's a condition called saturation where IC is no longer beta times IB. So, but we'll deal with that later. Right now, let's focus on active mode. So IS is given. So therefore, so from equation of IB equal to ISE to the power VBE over VT. Of course, it didn't say VT, so we can assume VT is 25 millivolts. Okay, millivolts, yeah. So if VT is not given, you can basically make that assumption. Do you guys see from this? S is given, IB is be able to find the only when you do the calculation is the unit. So if you want to use microamps, use microamps. If you want milliamps, you use milliamps. But don't mix them up. If you mix them up, you have trouble getting the right answer. So in this case, if we take divide IS on both sides, then we get IB over IS equal to e to the power VBE over VT. And then we take a logarithm on both sides. So we have VBE over VT equal to log IB over IS. Now, because IB and IS both given, so the easiest way for you to calculate to make sure you get the right unit is you can convert them into because IB is 10 micrograms, which is 10 times 10 to the minus 6, right? So it's a 10 to the minus 5. Divided by IS is 10 to the minus 15. So basically you have 10 to the 10 to the 5, 10 to the 10. Here, take a logarithm. And take that logarithm and multiply VT is 25 milliohms, and you get VBE, which is in milliohms. But you want to get a volts, divide by 1,000, you'll get volts. I want to stop here for a little bit. It says VB is of today's class, I said, if VB is larger than 0.7, it's going to be in active mode. If it's less than zero, I mean, it's going to be on mode. If it's less than 0.7, it's going to be off. Actually, that is really just an approximation. In fact, this transistor is going to conduct around 0.7. It could be slightly less than 0.7 or more than 0.7. That actually this VB is going to decide how much current flowing in. Okay. So remember when we studied diodes, we had this term called this diode has a 0.7 volt drop at 1 milliamps, or it has 1 milliamps at 0.7 volt. Remember that, right? So what it is said that this diode is going to conduct 1 milliamps with a 0.7 volt drop. But if your current goes beyond 1 milliamps, that 0.7 is going to become 0.705 or 71 something. But if the current reduces below 1 milliamps, the voltage is going to go down to 0.695 or something like that. Similar is true here. So don't argue with me saying, well, you said 0.7 is conduct, it's not conducting. Well, again, that is just like a rough number, which gives you a sort of first like judgment onto a transistor. The actual value is going to be decided by this equation. So once we find VBE, we can find current IC. And once we find IB, because IC is beta times IB, IB is 10 micro times 100. So that gives you really just 1 milliamps. Now we can find VCE, because VCE is VCC minus IC times RC. And VCC is 5 volts minus, how many? 3K. So 1 milliamps times 3K, that gives what? 2 volt. So this is larger than 0.3 volts. We got the voltage or VCE, which is then you find that this VCE got to be wrong. It's not going to work, right? So if I do say if RC equal to, let's make a simple example, 5 kilo ohm, we tell IB still 10 micrograms. Because IB is still 10 micrograms, so VB didn't change, so you don't have to do that. If IB changes, of course, that change. Now let's go to VCE. How much VCE is going to be? So let me redraw the diagram in this corner so you understand what I'm talking about. 5 volts and 5K ground. So VCE, it's going to be VCC minus IC times RC. Now, since beta is 100, so we know that IC is going to be beta times IB. It's going to be 1 milliamps. So that one was given by the definition. So now the 0 volts. So what I'm saying that VCE is only 0 volt. Do you think it is possible? This thing is not in the active mode. So this, if it's not possible, but things I can show you what saturation means. Now it is going to saturation, which means okay, we zero matter. So this is a number. So this is not in active mode, but IB is so it's conductive, but it's not inactive. What else can it be? So in the saturation, we see is given a 0.2 or 0.3, doesn't matter, but let's use 0.3 because H is 0.3. Like it's absolutely saturated, it's going to be 0.2. So let's use 0.3. It's not going to cause a big difference. So if we see 0.3, now IC is going to change because if you look at the circuit here, we know the top is 5 volts, 0, and we know how much voltage drop on the resistor. It's a voltage difference between 5 and 0.3. So IC is going to be 5 minus 0.3 divided by the top voltage minus bottom voltage divided by the resistance. And this gives you 4.7 divided by 5. That gives you almost 0.9, let's call it 0.97, 98, or actually 9.4, 0.94 milliamps. Actually dropped. Actually, now what I'm going to do is I'm going to take beta. I'm going to get a symbol called F. Because the relation between IC and IB is called beta. In the active mode, it's 100. But now it's in saturation. I want to see how much the relation is going to be. So that's going to be 97 divided by 10 micro. So that's milli. That's going to be 97. And that is less than 100. So this is called forced beta, which means while in saturation, that relation between IC and IB is no longer going to be 100, it's going to be smaller. So this example says if we have 5K, it did drop a little bit, but not so much. 97 and 100 just only dropped 3%. But if you look at the example that was given you, it says what resistance value needed to result in the same open, blah, blah. Replace the current source with a resistance connect from base. Oh, that's a different one. But if we increase the current, like by, if RC start 5, we set to 10K. You know what happens now? So you imagine the resistance is much bigger. So now your current, it's going to be in saturation mode. So now your current becomes 5 minus 0.3 divided by 10. So that's 0.47 milliamps. So let's say if. And then your beta F becomes 0.47 milliamp divided by 0.01 milliamp. That gives you 47. So if I keep increase the resistance at the collector, my current at the collector is going to keep dropping. Now your beta, well, forced beta is only 47, less than half of its value in active region. Okay. So that's important. Now let's move on to talk about the second part of the equation. Let's read it again. The second part of the equation says, replace the current source with a resistance connect from the base to 5-volt supply. So what it is says that, I'm going to draw it here, sorry. I run out of space. So this circuit says, this is going to be also 3K, 5 volts, and this is ground. So instead of connecting a current source, it's going to connect to 5 volts and how many kilo ohms? Oh, it says like they want you to calculate IB and to realize the same current. Now, as one approximation is that you can approximate this to be 0.7, so you can calculate IB equal to 5 volts minus 0.7 divided by RB. So that's kind of the very simplified calculation. You can do active mode. Basically, the because its IB is 10 microns, so we can calculate IB. But that will give you a value that is close enough to what you, but it's still not exact. Because as we calculated earlier, this equation really satisfies for that microamps. What you want to do, the more accurate value will be RB equal to 5 minus 0.69 divided by 5 microamps. That gives you a certain resistance, which is roughly 4.31 K, right? I think, yeah, so, oh, actually not 4.31 K, it's going to be 431 K, 431 K. It's a very small microamps, okay? So that's this example. And you see, especially when because it's really hard to understand why do you do that, right? So if you don't get it, that's fine. But just use the MOSFET, just use the BJT symbol. So in this example, it tries to give you like circuit and that equivalent circuit to calculate, which is, I didn't use it, but I still get the right answer. So you don't have to do that. You can, but you can if you want. If you understand the circuit, equivalent circuit, you can do it. So this side, you get a equivalent diodes current coming in, and that side you have beta times IB, which is current, and you have resistor at the top, right? So that's for the part one. And for the part B, instead of current resistant, it's give you the same answer. So far, like early on when we talk, that is very different from the way we make MOSFET. Remember, when we make MOSFET, we get a single piece we dig a hole and we connect. So BJT later on format, you use a substrate build N-type substrate. So on that, you dig a well, you dump material, you the N-type material. You have now you have N, P, and then you have E, B, and C, which each one of them is connected. So BJT is not a bidirectional device. Remember, it's bidirectional because we have you like, remember the MOSFET we built. I just want to draw the same thing here. So the MOSFET it builds a channel. Because the MOSFET is electrical, bidirectional device. But a BJT is not a bidirectional device. Current can flow from collector to emitter. Remember that. So direction. So the way you build the it makes the the manufacturing process, like the fabrication of fab, easier. But the sandwich will reach. So let's look at this another way to represent the saturation. BJT, when we say VBE is less than 0.3 volts, it's in saturation mode. So if you look at this, at the bottom, we on the emitter. So if the emitter is grounded, I'm going to draw another diagram over here to emit. So if this is grounded, so from here to here, it's 0.7 volts. But from here to here, it's 0.3. We're talking about the saturation mode. So what do you think about the collector voltage? This becomes very interesting because 3 volts, but from here to here, 0.7, which means the collector voltage is actually less than the base voltage in the saturation mode. So this is 0.7, this is 0.3. So from A to B, VCB is actually 0, here to here is minus 0.4. So that's how push this expression here. If we draw VCB on the horizontal x as a function to more. So this is just a different express. So VC is lower than VB. VC is lower than VB in saturation mode. It doesn't really explain anything else. This diagram itself is not so much more information for you. Back to look at how we had this diagram. We want to draw the complete, like the model for operation is that you have N, and you have P, you have N. Right? So, and then once you have current, this P. So when you connect the voltage to the chain junction here is forward bias. Electrons move. We got injected electrons move to medium. It's going to break. You have two diodes. So one is here, another is here. So that's the equivalent. So, B here. to from C to E and from B to diodes. But that dB is working in a forward region. That DC is working in the breakdown region. Okay. So again, just sort of explaining the relations. Now we can go back also to look at, because you can build NPN, you can also build a PNP. So PNP is built just over there. You have a piece of P material on top, you build N, and then on top you build P. So this becomes a PNP material. In the PNP material, you also have when we connect a current from base to collector, we start to flow current from base to collector. And then that current keeps electrons to move, but in this case, it's not electrons, but holes. So holes moving from, so hole means move from break down this pin junction so that the holes move from this side to this way. So you have a current going collect. And symbol for PNP is exactly the mirror, like top-down mirror of NPN. So if I draw here NPN, so that's by side. This is the current from emitter, but is from emitter. So if you look at the relations between, for this one, you see from emitter flowing down, it's collector and base. So therefore, you still have IE equal to IC plus IB, the same thing. And then you have IB equal to beta times IC. So those equations, I mean, for both PNP, emitter, that from emitter to collector. But to make it like, I would say still say please our eyes to make it they feel normal. So we drawing the current flowing from top to bottom. Okay. So here. Yeah. The difference between this one is that for the NPN, current flowing into the base, but for NP, current flowing out of the base. So that's the difference between this. They're almost the same. So that's kind of covering the very basics of BJTs. So now we're going to move on to talk about the current and voltage characteristics, mostly through some examples. Okay, so I made a table here. Let's kind of build a table to look at the relations. So the voltage is here we call VCE, now we call the VB becomes VB. And things that are flipped. Everything just flipped for the type of device. So now let's look at the first equation will be the relation between off and on state. So for this to be off, for NPN, our VBE has to be larger than 0.7 volts. So that's, I mean, less than. And for PNP and VEB would be less than 0.7 volts. That's for the off mode. And of course, for on mode, you will have VBE. That's what you're going to talk about. And then in the saturation mode, you have VCE, less than 0.3 volts. And here you says VCE, VEC. VEC is less than 0.3 volts. And in active modes, it's just opposite. So VCE larger than 0.3 volts, and this is VEC larger than 0.3 volts. And then we have the current IB in the saturation, in the active mode, we have IB equal to IS times E to the VBE over VT. And then for the PNP, we have IB equal to IS times E to the power VEB over VT. So we again flip the VBE to VEB. And finally, we have IC. So we have IC equal to beta times IB. Same thing here, beta times IB. And probably the final one, we're going to say IE. So IE equal to IB plus IC. And here, same thing, IE equal to IB plus IC. So this kind of to summarize what we covered so far, to start the transistor, we saying, is it off or is it on? If it is on, is it in saturation or is it in active? If it's in active, what is the voltage? What is the current? What are the relations? So this gives you the very detailed process to analyze the circuit. So this is the sort of, so we're gonna spend time over here. Oops, there, okay. There's another presentation to look at the voltage relations we saw earlier. Therefore, for example, PN, B2E is 0.7. Again, of the different modes is going to or less, it's in saturation mode. but it can be more than like 0.3. So this, so it's going to really, yeah, we see larger than 0.3, it's more, so it will be in active mode. So like, once you do that, you're going to be in saturation mode, in active mode. Okay, so summarize again the different relations, IC and IB and IE. And for PNP transistors, replace VB with VEB and so on. So that's all kinds of relation. And down below, you have VT is 25 millivolts on that. So really, it's kind of you guys so far mostly get a NPN transistor relations, right? So mysterious about BJTs, very simple. There's VBE, there's VCE, and there's a relation between IB and IC and IE. So those are the only basics of BJT. So taking like all this, write this in your brain, and you will be able to solve any problem, regardless how complex the circuit is, regardless how many BJTs in that circuit, because you can always isolate the circuit and then do a simulation. Of course, when we move on to the multi-stage, in another class, you'll see, well, it's not going to be that simple because there's one current flowing here, but then the current combined with the other one, and you don't know this one, you cannot find another one, so you have to go back to like do iterations, to get the final answer, or you can simulations. But in this class, apparently we don't get to that. So mostly you guys are going to be able to solve the problem by using this set of equations, right? So let's do an example. So in this example, VB is given and VB is 0.7. Okay, so here you guys see this term again. VB is 0.7 at 1 milliamps. So this is a typical description of a diode. It says that this BJT has a typical diode performance. When you have VB is 0.7, you get IC is 1 milliamps. So what really all says here is that if I go to IC equal to IS VB times VT, right? So then if VB is 0.7, IC is 1 milliamps, VT is 25, what can you solve for? IS, right? So you can find IS. So if you find IS, which means you got IC2 is 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 given, and E to the VBE, you have a different VBE, you can find that IC2. So that's what it already says. Give this 1 milliamp at 0.7 volts, 0.711 milliamps. You can find IS. Now you can find current for any VBE, or for any current you can find VBE, or for any voltage VBE you can find IC. Right. So it says that design the circuit so that 2 milliamps flowing through the collector, a voltage drop of 5 volts. So voltage drop 5 volts flows through the collector, and voltage of 5 volts appears at the collector. Actually, no. Actually, this is not right. It didn't say that. It says here. It says the voltage here is 5 volts. We don't know the voltage over here. We call VE. So the probably easy mistake to make is that assuming VC is 5 volts in this case, which is not. Okay, so if VC is 5 volts, and the top power supply is 15. So at least you can get an RC right away without knowing even the performance of transistor, right? Because you have how do you calculate IC? Right? I mean, how do you calculate RC? So RC will be 15. How did I write that? So RC equal to 15 volts minus 5 divided by current IC, and IC is, so you get 5 kilo ohms. That's something that you can calculate right away without even knowing the transistor, because the voltage is given and the current is given. But the next step is going to see what we B is grounded, so VB is B minus VE, so VE must be a negative number. VE must be negative. And for the first assumption, if you assume, because if we assume this thing is in active mode, and we also assume that VBE equal to 0.7 volts. If we do that, we can say VE is negative 0.7. Now we can calculate IE equal to VE minus 15 divided by 2 milliamps plus IB. For better, H is 2, so this is going to be 0.02. 0.02. So it's like 15 minus 0.7 divided by 2.02 milliamps. That gives you certain kilo. So what I did here is I assume it's active. I assume VB is 0.7, so I got this answer. We think that we didn't use that VB 0.7 at 1 milliamp. We didn't use that. That's the problem. So the answer here, even though it's good enough, but it's not the exact answer. It's like a little bit, it's a little bit off from the actual diagram. So you know, to get the exact answer, what we need to do? Well, from the top, so you guys already see here. So all you need to do is to calculate IS from that 0.7 and 1 milliamps. So here, so from 1 milliamp, 0.7 volts, you calculate IS. So that's step 1. And step 2, next, it says it's 2 milliamps, right? So from here, you can say, okay, so 2 milliamps go to IS, because IS already so we need to. So that VB2 will be the exact this transistor. So but once you find So now you find VBE2. So VBE2 equal to 0 minus VE, right? So then, which means VE equal to 0 minus VBE2. But of course, you find this VBE2 slightly 7. So 1 milliamp would have been 0.7 volt, but since it's a little bit more than, it's 2 milliamp. This value is pretty close to the one that we calculated earlier by assuming it's 0.7. But of course, when you do a problem, you have to do the second step because it was asking you the exact value. But in the design phase, the first pass design, yeah, and we find exactly the value. You find here, so we be the exact solution 0.1 IE, of course, this are slightly, slightly bigger, slightly smaller. We assume it's 0. Okay. And now we're going to go through another example. The voltage at the emitter was measured minus if IE, IB, IC. So this should be simple. It is. Careful whether it's in a saturation or whether it's a linear mode, because we don't know. They want you to find VC. So if you find VC later on is different from your assumption, yeah. For BJT, almost all the time, you start by assuming it is in the active mode to do the problem. But there's nothing wrong if you assume it's in saturation. It's okay too. But let's do maybe both, and you guys can get a better feeling of what we number one. So assume in active. So if we assume active, it says VE is 0.7. So VE is minus 0.7, which means VBE is 0 minus 0.7. So apparently, transistor is be in conduction mode. It's just we don't know what it. So if this is in 0.7 volt, we can calculate I. Why? Because it's 0.7. We basically already know voltage from V to minus 10. So that's that I. Right? So we can use minus 0.7 minus 10 divided by K. That gives you 0.93. 0.39 milliamps. So once you find IE, we can find RC. RC equals alpha times IE. Alpha is 50 divided by 50 plus 1 times 0.93. That gives you 2.9. Now, uh, you know, IC, we can simply find out VC is going to be 10 minus R. So what's 10 volts minus voltage drop on a 5K resistance? VC times 0.93. How much you to get? 465, right? 465. So we got about 5 volts. So now we can do, we found that voltage at VA, and we also know voltage at VE. So we can now calculate VE is minus 0.7, okay? So you got that correct. So now you got 6.15 volts. This is apparently larger than 0.3 volt. So is inactive. So this last one is actually important because what we're doing is we verify that the transistor is working in the mode we started. If the problem. So you might say, okay, well, this one we did by chance, we assume it's actually inactive. So if you started, let's say, in saturation, I guess this also tells you a little kind of process. If you assume it's a saturation, how do you do the problem? Now, if we do assume it's in saturation, we still know that VE is minus 0.7, which is still correct. VE is still minus 7 because that one 0.3. So if 0.3, minus VE is minus 0.4 volts. So that's it. Because now the 0.3, because that's because we assume it is in the saturation mode. So now you get VC, we can calculate IC equal to 10 volts minus 0.4 divided by 5K. That gives you 10 9.6, right? So 0.48 milliamps. So now we found IC, and we can calculate IB, which is IC over beta. So you find IC over beta 0.48 divided by D, because like almost 0.01 milliamps. Let's do that. Now you can find IE equal to IB plus IC, which is equal to 0.49 milliamps. So this I want to highlight because early on we can from here IE, which is impossible. So which means this got to be wrong. This got to be wrong. So I see than this. So I mean, IE, one of them has to be bigger, right? So, but typically IB, it doesn't change. So IC has to be bigger, which means this is not in saturation and not in saturation. So we got to conclude. So at this point, you would go back, find something is wrong, go back to assume it is in active mode and redo the problem. Okay. So sometimes, of course, based on the problems given, you might start with one assumption, you got it right, done. But you started with one assumption, you did the calculation, it's not right, you go back to redo it, so two pass. Okay. We don't know in the beginning whether it's in saturation or active. So we have to start with one assumption and find whether it's correct or not. So that's 6.13. Let's do another problem. This is a PNP. This is sort of give you a kind of a flavor of what happens if it's a PNP, it's not an NPN. So now it's what it is said is that the measurement is given. So VB is 1 volt. That is a given number. And VE is 1.7. So it's quite good. Some numbers given. And they want you to find beta. They want you to find alpha and VC. Okay. So first of all, VE is 1.7 and VB is 1. So we so the first step, we can conclude that this transistor is on. It's not cut off. If it isn't cut off, right, stop. Right, it's not in cut off. We have to move on. So the next step is how we need to find beta and alpha. We see. So now, because that, you see, that VB is given at 1 volt. The resistance also given at 100 kilo ohms. So right away, we can calculate IB equal to 1 volt divided by 100K. So this is how much? 0.001 milliamps. So it's 10 microns or 0.01 milliamps, right? What number can be found is connect. Some this may not be accurate anymore because it's another current. But here you really have just a current, and the current flows from emitter to base and to ground through that 100K. IB lady. E. So you find IE. But that- now we plug in the minus 10 plus 5K times IC. That I is given, so we need to find a beta. We should be able to one problem that again, because we know IE and ID, so we should be able to find a beta. So we find a beta, we plug in beta, we find IC, and then plug IC, we find VC. So at the end, what we need to do is we find VEC has to be larger than 0.3 volts. If it's not more than 0.3 volts, we have to redo the problem right now. So just recap. You can remember plug in, find IC. Once we find IC, we plug in here, we can find VC. Once we find VC, we can calculate VCE. That has to be larger than 0.3. So yeah, so and is minus 1.75. Okay. Okay, so